Hello, welcome to this lesson in the Linear Algebra Tutor. In this lesson, we're going to switch gears a little bit and we're going to start to talk about how to use matrices to solve systems of equations with something that we call row reduction. I'll explain what row reduction is in just a minute, but basically what we're going to learn about in this section and the next several sections is really one of the most important reasons that anybody learns about matrices. And that is the concept of solving a system of equations. You know, whether you're an electrical engineer, a mechanical engineer, chemist, physicist, doesn't matter. Eventually you're going to have what we call a system of equations to solve, which means you might have 3 equations and 3 unknowns, or you might have 2 equations and 2 unknowns, or you might have 6 equations and 6 unknowns. And so you learn in basic algebra how to solve those systems. You might use substitution, you might try to graph them and see where they intersect or whatever, which is fine for small systems, but for large systems with 4 or 5 variables, it's very difficult to apply substitution or graphing methods to get to the answer. So matrix methods can be applied to any system of equations, any linear system of equations, where we have multiple unknowns and multiple equations. The other thing I want to mention here is I'm covering this here along with the next several sections for completeness, because you're going to be asked to learn how to do it in your class. I have also covered a lot of this material in detail in what I call my matrix algebra tutor. So when you get done with this set of lessons here on solving systems of equations, if you want even more practice, then I encourage you to go get my matrix algebra tutor where I have more examples. But make no mistake about it, we're going to be taking that material, doing that, and we're going to be diving a little bit deeper in this linear algebra class, because we have to go to a little bit deeper level to get that to get that understanding of a university level linear algebra class. But we have to crawl before we can walk, so let's talk about a system of equations. So here might be a system. 2x plus 5y plus z is equal to 5. Now this is one equation with 3 variables. So my second equation might be x plus 4y plus 2z is equal to 1. And my third equation might be 4x plus 10y minus z is equal to 1. So you all should know by now that this is 3 equations and 3 unknowns. Now, in order to have a hope and a prayer of solving this for a unique x, y, and z, you have to have the same number of equations as you do unknowns. All right, as you do unknowns. Now, it doesn't necessarily mean that a solution is going to exist to this. It's very possible that what this represents, that they don't intersect in such a way that you're going to find a solution. In 2 dimensions, it's pretty easy to think about. In 2 dimensions, just x and y, you're drawing a line and you're drawing another line. The intersection of those lines is what we call the solution. But of course, I could have a line here represented by one of my equations and another line exactly parallel to it, in which case they'll never cross. So that would be, you would attempt to solve it by substitution, but you would run into problems even if you try to solve a system with parallel lines like that, even in terms of matrices, because those lines don't cross anywhere. So there's really no solution where they intersect and have a common xy value. But in any case, you cannot tell from looking at the system of equations if it has a solution, but you know that in order for there to even be a chance, you have to have 3 equations and 3 unknowns. You have to have the same number of equations as you do unknowns. All right, now this is linear algebra, so we're talking about matrices. We can represent this system of equations in terms of a matrix. We can write as the following. We can write it as the following. We can write it as 2, 5, 1, 1, 4, 2, 4, 10, negative 1. Notice that what I have done here is I've just taken the coefficients from my set of equations, the 2, 5, 1, 2, 5, 1, and so on, and I've transcribed them out into a matrix, right? So this is what we call a coefficient matrix, and typically you'll see it in a book written as matrix A. That's the coefficient matrix of your system of equations. Now I can multiply that by another matrix that contains the variables I'm trying to solve for, in this case x, y, and z, so I'm going to write that as a column matrix like this. Typically you represent that as capital X. So I'll come back to this in a minute, but basically your unknown is this entire matrix. We have to pick something to represent the matrix, so we use a capital X. But we know that that matrix X really contains all of the variables that we care about, in this case x, y, and z. It could be A, B, C, it could be x1, x2, and x3, but in any case we refer to the unknown You might think of it as a vector, by the way. You think of it as an unknown set of values. We call it capital X. And then we have to set this equal to something because there's an equal sign here. And on the right-hand side, we put what's on the other side, 5, 1, and 1. And this matrix is called the B matrix. Okay? This is called the B matrix. So basically, the bottom line is, you might see in your book a lot that you can represent any system of equations by A, matrix A, times column matrix X is equal to B. It's a very, very compact way of writing something that contains a lot of information. Matrix A is the coefficient matrix of my system of equations. This is a column matrix that contains all of my unknowns. And this is a matrix with everything on the right-hand side of the equal sign, also a column matrix. All right? Now, why is this representation equivalent to this? Because if I multiply this out, I'm going to go over and down. So 2 times x plus 5 times y plus 1 times z. That's over and down. That's exactly what the first equation is. It's equal to the first number up here, 5. So if I go over and down, I've basically replicated this first equation equals 5. If I go over and down here, 1 times x plus 4 times y plus 2 times z over and down equals 1. I've replicated the second equation. And also for the third equation, over and down, 4 times x plus 10 times y minus 1 times z is equal to 1. That replicates the third equation. So the reason that you can do all of these solution methods that we use with matrices is because we can write a system of equations in terms of a coefficient matrix, an unknown variable matrix called x, and a B matrix, which is what's on the right-hand side of the equal sign. Doing the multiplication recovers the original set of equations that we care about. All right, now we can write the set of equations like this, but we can also represent this system as what we call an augmented matrix. See, so far we talked about matrices, and that's just been a collection of numbers. An augmented matrix is the following in this case. Let me show you what an augmented matrix is. So I'll put augmented matrix. Now the word augment means to enhance or to further along something, to add on to something. That's what the word augment means. So we're taking a matrix and we're adding something to it. That's what that means. So the augmented matrix for the system would be 2, 5, 1 with a dotted line, and then we put what's on the right-hand side of the equal sign right there. And then we have 1, 4, 2, 1, 4, 10, negative 1, 1. When you see the word augmented matrix, the dashed line here means that everything to the left is the A matrix, everything to the right of the dotted line is the B matrix. All right, so you can also see that written in books a lot of times as A with a line and then B. This is the coefficient matrix. This is what's on the right-hand side of the equal sign. The reason we're writing it like this is because I'm going to teach you how to solve systems of equations with what we call row reduction. And in order to use row reduction, we're going to use the augmented form of the matrix, because the augmented form contains all of the information about the coefficients of my system of equations, and it also contains everything on the right-hand side of the equal sign, and it's all wrapped up in a nice bow in one singular matrix. So we want to keep everything together so that we can solve it. All right, now we're going to talk about row reduction, or matrix row operations. Basically, this matrix, including what's on the other right-hand side, is equivalent to our system of equations. But it turns out that we can perform mathematical operations on the rows of this matrix. And even though the matrix might look a little bit different, it's still going to represent the same information as this original matrix. I mean, when you think about it, if you think about a regular old equation in algebra, right? Let's just take a little aside here, just give you a little motivation. What if I give you, 3x plus 12x is equal to 4, right? 3x plus 12x is equal to 4. Or actually, let's do it like 3x plus 12y is equal to 4, some sort of equation. You know from algebra that you can factor out number here. So I can pull out a 3, and I can make this x plus 4y is equal to 4, right? All I've done here is I've taken a 3 out from here and a 3 out from here. And you can back multiply and verify this gives you 3x and this gives you 12y. So you know that the second line here is exactly equivalent to the first thing. They look different. If you ask any third grader if these two things are the same thing, they're always going to tell you no. because this looks different. It's got parentheses in there, it's got different numbers. I mean, you have a 4 here, there's no 4 on this side originally. They look different, but yet we know from the rules of algebra that they actually represent exactly the same thing. All right, so what we're going to be doing with this augmented matrix is I'm going to show you the legal row operations to transform the rows of this matrix. It's going to look different, but the matrix will still represent our system of equations. Just like this represents our original equation. It's an analogy, but it's very appropriate. It's very, very similar. So let's talk about matrix row operations. Matrix row operations. There's really only 3 things that you can do to a matrix as far as their rows, such that it's legal and it preserves the integrity of the matrix. The first one is you can interchange 2 rows. Now at first, interchange meaning you swap their location of the rows. Okay? Now first you might think, well, how is that legal? You can swap the rows, aren't you changing the matrix? Well, you are changing the way it looks, but don't forget, what does this augmented matrix really represent? It represents one equation up here equal to 5, another equation here equal to 1, and another equation here equal to 1. So if I were to swap row 1 with row 2, the matrix would look different, but it would still represent the same set of equations. Because if I move this guy up here, I would just have this equation in the top row of the matrix and this equation in the middle row of the matrix. But I would still be representing all 3 equations. I haven't lost anything by switching the rows like that. I have simply changed the way the matrix looks. Now the second thing that you can do is you can multiply a row by a non-zero scalar. All right, so you might be thinking, well, geez, if I take a matrix, I can actually multiply a row by 5, by 6, by 4, a non-zero scalar. Maybe I multiply by -1 or -1/3. How is that preserving the integrity of the matrix? Well, sure, if I multiply this by 10, this row by 10, I would have to multiply this element by 10, this element by 10, this element by 10, and this element by 10. And yes, the matrix would look totally different, but it would still represent the same system of equations, because if we go up to here, this equation is 2x plus 5y plus z is equal to 5. You know from the rules of algebra, you can do anything you want to both sides of an equal sign in an equation. So sure, I can multiply this by 10 as long as I do it to both sides of the equal sign. I've still represented and contained all of the information in that equation, even though I've altered the numbers. All right. The third thing you can do to a matrix is you can add a multiple of one row to another. You can add a multiple of one row to another. So that one's a little bit harder to visualize, but if you remember back from algebra, when you solve systems of equations, you can add the equations together because you're essentially applying and doing the same thing to both sides of the equal sign. You're treating it as a set and you can add them together and you're arriving at kind of like a new equation that encompasses the original 2 equations and all the information in there. And so you can do the same thing here. So these are what we call matrix row operations. You can interchange 2 rows, you can multiply a row by a scalar, you can add a multiple of one row to another. Those are the only 3 things you can do. If you do something besides that, you've screwed up the matrix. But if you do these 3 things, then you can manipulate that matrix and make it look different, but in fact it will represent the same information. So at this point in the game, we need to solve this system of equations, because then you'll understand and solidify what I mean by row reduction techniques. So what we want to do, first of all, is we want to take this augmented matrix, the one here, down here with the dashed line, and we want to do these row operations, and we want to get the following thing. We want to do multiplications and additions and all that stuff so that we get an identity matrix on the left, and we're going to get some numbers which we don't know yet on the right. All right? So basically we do row operations until we beat the left-hand side of the augmented matrix into an identity matrix. Now you know why I introduced identity matrix, so you understand what this means. And in the course of doing that, of course, everything on the right-hand side of the equal sign or the dashed line is going to also change. But once you get everything into this form, you can read the solution directly off the board. Because X, that would be the first guy here, would be equal to this number, Y would be equal to this number, and Z would be equal to this number. So we get it in diagonal form so that we can read the solution for X, Y, and Z directly off of our newly constructed augmented matrix. So it's a little bit like Tetris or some kind of puzzle game. You're trying to manipulate that left-hand side to equal this so that you can read the solution directly off the board or directly off of your calculations. So without further ado, let's do it. We're going to have, let me start here. So what we're going to have is the original matrix. You know what I'd like to do first? We know we're going to get to this form. Let me just kind of erase this, give myself a little more room. We know we're trying to get to a diagonal matrix on the left-hand side. And now what I would like to do is start by writing down the augmented matrix that we already talked about. So we have 2, 5, 1, 5, 1, 4, 2, 1, 4, 10, -1, and 1. This is the original augmented matrix. Nothing has changed. This is exactly coming from our system of equations. We've done nothing yet. All right? Now what we want to do is start working, and I'm going to start working down the board here. I'll try to swap colors every now and then too. All right, so we want a diagonal matrix. We want 1s along the diagonals and 0 everywhere else. So the very first thing you do is you try to get a 1 in the upper left-hand corner. Now I can start dividing and stuff to do that, but the easiest way to do it in this case is I already have a 1 here, so let me just interchange row number 1 with row number 2. That's totally legal according to my rules. So what I'm going to do is I'm going to draw a new matrix underneath it. I'm going to take this row and put it on top. 1, 4, 2, 1. This row, I'm going to swap it and put it in the middle, 2, 5, 1, 5. And this one, I'm going to put 4, 10, -1, and 1. And it's very, very important for you to write a note to yourself what you did to get from this matrix to this one. So I'm going to write row 1 with a double arrow, row 2. So there's a couple things I want to explain to you here. This notation means, with the double arrow, means I have swapped rows 1 and row 2. That's what that means. And I'm also writing it on the line for row number 1. That tells me that I've done it to this row here. All right? Now let's go underneath it and figure out what do we need to do next. Now we have a 1 up here. What you want to do next is you want to get zeros underneath your left-hand column. I'm trying to tell you, there's more than one way to do this. The row operations are the legal thing you need to do, but you can have some freedom in how you apply it. I'm trying to show you sort of the cut and dry way to get there. The first thing you want to do is get a 1 up here. After that, you want to start getting zeros underneath your 1. So let me draw a new matrix here, and let's figure out what we need to do. Well, if I want a 0 here, first of all, let me write this guy. I'm not going to change anything in my first line. I'm going to leave that alone. But in the second line, I want to get a 0 here. So if I multiply the first row by -2 and then add it here, the way I would write this guy is -2r1 plus r2. Notice my notation. I'm multiplying the first row by -2, that's this row, and then I'm adding it to row number 2. And I'm putting this writing on the second line. That tells me that I'm doing it, and I'm putting the answer in this line. So it's very important where I write it to tell myself what I've done. So if I multiply this by -2 and add it to this, I get a 0, which is what I want. If I multiply this by -2 and add it, it will be -8 plus this, which would give me -3. All right, if I take -2 and multiply by this, I'll get -4 plus this will give me -3 right there. And then if I multiply this by -2, that'll give me -2, adding to this giving me +3. So you got to be a little careful when you do this, and you can expand these steps if you want to write down the additions and stuff inside, and that's okay. But I think at this level, I think you can handle a little bit of multiplication and addition in your head, but you do need to be careful because there's going to be a lot of steps getting from matrix number 1 to matrix number 4 or 5 over here when we get to our answer. So you want to make sure that you're doing the right math and you kind of check yourself as you go along. So I would go back and check everything after you've written it down to make sure. Now the second thing we want to do is we want there to be a 0 down here. So in order to do that, we want to multiply this by -4 and add it to this so we get a 0. So I'll say -4 times matrix R, or row R1 plus R3, and I've written it on the line with R3, so I know I'm doing it to that guy. -4 times that, adding it to that gives me 0. Negative 4 times 4 is negative 16. When I add it to this, I get negative 6. Negative 4 times this is negative 8, plus that is negative 9. And negative 4 times this plus 1 is negative 3. All right, now you can sort of see where we're going. We started with this matrix, and I'm telling you that switching the rows gives you a new augmented matrix, which is exactly equivalent to our system of equations. And we do these row operations, and these matrices are all said to be row equivalent. And that means after we do these operations, the matrix looks different, but it's still representing the same thing. This matrix looks quite different, but it's still representing the same system of equations. Now we want to keep going and get diagonals everywhere with a 1, and we want to get zeros everywhere else so that we can get to our answer. All right? And so the next thing we want to do is we want to, I'll just switch to red, and I'll go down below it, and I'll say here's our new matrix here, down below here. Now, the next thing we want to do is put a 1 right here. So the way you do that, first let me just write we're not doing anything here, so I do 1, 2, 1, 4, 2, 1, like that, all right? And then we want to get a 1 there. So how do we do that? We multiply by negative 1/3 times R2. Now notice I'm writing it in the second row. When I multiply negative 1/3 times this, I get 0, right? When I multiply negative 1/3 times this, I get positive 1. When I do the same thing here, I get positive 1. When I do the same thing here, I get negative 1. All right? And then I'm actually not doing anything to the third row. 0, negative 6, negative 9, negative 3. But I'm getting there. I've got diagonals both with the number 1. All right? And now what I'd like to do is move myself up and bring this all the way over to the other board. So what I'm going to do for clarity is I'm going to rewrite exactly my last matrix, the last known matrix that I had. I'm going to rewrite it there. And I had 1, 4, 2 with a 1 here. And then I had 0, 1, 1. And on the right-hand side, I had negative 1. And then I had 0, negative 6, and negative 6, negative 9, and then negative 3. So this is exactly the last step that I had. Now let me go below it here and try to see what do I want to do now. I want to make this a 0 underneath this 1. I want to make that a 0. So let me go and open this guy up. I'm going to copy 1, 4, 2, 1. Right? I'm not doing anything to that. I'm also not doing anything to this row yet. But I am to the third row. I'm going to take 6 times R2 and add it to R3. 6 times R2 and add it to R3. The reason I'm doing that is because when I take 6 times this and add it to this, I still get 0. 6 times this gives me positive 6, plus this gives me a 0. 6 times this gives me 6, add it to this gives me negative 3. 6 times this gives me negative 6, plus that, negative 9. Okay, so you see what I'm doing? I'm inching my way over. Now what I want to do is I want to get this guy to have a 1, because remember I want 1s along my diagonal. So what I'm going to do is redraw the matrix below it. I'm not going to do anything to the top. I'm not going to do anything to the middle. But on the bottom one, I'm going to take negative 1/3 times R3. When I multiply it times 0, I get 0. Multiply it by 0. When I take negative 1/3 times this, I'll get a positive 1. Negative 1/3 times this will give me a positive 3. All right, so I'm halfway home, really, because now I have diagonal 1s and I have zeros underneath it. All right? Now what I need to do is somehow get a 0 here, a 0 here, and a 0 here. And the easiest way to do that is to first work on these two guys and getting them 0 right there. So if I take this guy and multiply it by a number and add it up here, I want to multiply by negative 2 and add it up here. So it'd be negative 2R3 plus R1. That's what I want to do to the top row. I want to multiply this by negative 2 and add it. Now, of course, when I take negative 2 times this and add it, I'm not changing anything because this is a 0. Multiply by this by negative 2 and add it, I'm not changing anything. But when I multiply this by negative 2 and add it, I get a 0. And when I multiply this by negative 2, I get negative 6, and I add it, I will get negative 5. Okay, negative 5. So that's right. Now for this row, I want to multiply negative 1 times this and add it to this, again to get a 0 here. So I will say negative R3 plus R2. 2. So I'm taking negative row 3, I'm adding it to row 2 there. When I do it to this and add it, I just get a 0. When I multiply by negative 1 here and add it here, I'm still going to get exactly what I had in this place. But when I take this times negative 1 and add it, I'm going to get a 0. When I take this times negative 1 and add it, I'll get negative 4. All right? And I haven't actually done anything to the bottom row. Right? Now there's only one thing left to do. I want to make this a 0. Once I've done that, then I've achieved exactly what I'm trying to do. I know it's been a long row, but stick with me. We're almost there. All right, and so what I want to do here, I'm going to work with this one, negative 4 times this row, and add it to this one. So negative 4R2 plus row 1. When I do negative 4 times this and add it, I'm going to keep the same thing. Negative 4 times this and add it, I'll get a 0. Negative 4 times that, add it, I'm going to get that. Negative 4 times this will give me positive 16. And when I add it to that, I will simply get 11. Right? And then I'm going to keep everything else the same. 0, 1, 0, 0, 0, 1, negative 4. And then we have a 3 at the bottom here. So I haven't changed anything with that bottom row. And now I promise we've gotten to the end of a journey. I know it's been kind of long getting there, but remember the whole point of doing this stuff was to get the left-hand side into an identity matrix, and the right-hand side just falls out however it does. And the reason we do that is because we can now read the solution directly off of what we have. Since these equations are something times x plus something times y plus something times z is equal to something, we can now we have zeros everywhere. We can read x is equal to 11, y, this guy, is equal to negative 4, and z is equal to 3. So I could circle these and I could say these are my values, or if I want to use matrix algebra notation, I could say capital X can be a matrix or a column vector, which would be 11, negative 4, and 3. This is two different ways of representing the same exact thing. I can write x, y, z, or I can say, hey, my unknown was capital X, which contained 3 values, which was my unknown, and it's equal to that. I know that it's a complicated thing. Row reduction, to be honest with you, is a pain in the you-know-what. Mostly, it's all just addition and subtraction and multiplication, but the problem is that if you make a mistake somewhere, it'll ripple through. You see, if I accidentally add something wrong right here, then it's going to ripple through, and eventually you're going to get to the end and you're going to have the wrong answer. So you really need to check your work as you go. The other thing, as I said before, there are numerous different paths to go to do row reduction and be legal about it, so you might pick a different path. I'm trying to tell you, through my experience, the fastest way to get there. So what I want to do first is I want to get a 1 in the upper left-hand corner. And then I want to get zeros down below. So I'll be multiplying this row times something and adding it to these two. That's what we did here. We had zeros down here. The next thing I want to do is get a 1 here, so that the following thing that I want to do is get, when I go from here to here, I want to get a 0 underneath here. Notice how when I do it this way, if I multiply this row by something and then add it to this, the zeros that I had here are not going to be influencing anything. I'm multiplying by 0 and adding, so I'm not going to cause any problems. When I get a 1 there, then I multiply and go down. So I get a 0 there, and then I get a 1 there. So I guess if I had to give you some advice, try to get your diagonal elements first, getting zeros down below first. Don't even worry about the top hand of the matrix until the end. That's probably the most important thing I can teach you. So again, start by trying to get a 1 here, get zeros underneath, then get a 1 in this diagonal, then get a 0 underneath here, right? And then divide to get a 1 here. So right in the middle of everything, you should have diagonal 1s with zeros under it. And then for the second half, you want to get zeros up here in these two first. So multiply and add, getting zeros here, and then use the middle one to multiply and add to get zeros there. Once you do that, you can read everything off. I'm not going to try to sit here and explain why doing it this way is best. It's really up to what you want to do. There may be other ways that you like doing it, but I will tell you this, that if you follow different paths, sometimes you can get into trouble. Like for instance, if you start trying to do things a little bit too early, like if you try to get zeros up here before you've done things down here, notice how when I'm multiplying this times something and adding it here, I'm not screwing up what I've already achieved with this 0 here because I already have zeros down here. So I guess what I'm trying to say is if you're not careful and you're not following an algorithm, so to speak, then what you're going to end up doing is messing up some of the zeros that you already achieved when you're trying to go out of sequence like that. So it's better to get the diagonal ones, get the zeros underneath them, then go get the ones up above, in this sequence. That's kind of my advice to you. So this guy has a solution, a unique solution, x, y, and z. When a system of equations has a unique solution, we call it consistent. A set of equations is consistent when it has a solution. So we call it consistent. And you'll later find out when a system of equations doesn't have a solution, we call it inconsistent. So you might be asked on a test, solve the system of equations, tell us if the solution is consistent or not. And you know what that means. So make sure you understand this, these row reduction operations. And basically what it boils down to is we're saying that this augmented matrix is really exactly equivalent to the first one we started with up here. And because of that, it allows us to read the values of the answers directly off. We're just inching our way from the first matrix on into the final matrix. We're going to do a couple more examples. So make sure you understand this and follow us on to the next section where we'll do that right now.